Welcome. Today we are prying open the lid on the AI Toolbox. We're going to look inside and really get to know the powerful, super specialized neural networks that are out there changing our world one very specific job at a time.
So, have you ever stopped and wondered how an AI can look at a medical scan and spot a disease? Or how it can predict where the stock market is headed? Or even just create a piece of art from scratch? I mean, how does it do all of these incredibly different things? Well, the answer isn't some single, all-powerful brain. It's way more interesting than that.
The real secret here is to think of AI less like a single entity and more like a well-stocked toolbox. I mean, you wouldn't use a hammer to saw a board in half, right? Of course not. And it's the exact same idea here. AI engineers pick and choose different kinds of neural networks, and each one is perfectly crafted for a specific job. So today, we're going to take a look at the most important tools in that box.
Okay, let's start with the real workhorses. These are the foundational tools you'd find in pretty much every AI workshop. They are the core architectures that power a massive range of applications we see every day. First up, we've got the Multi-Layer Perceptron, or MLP for short. Just think of this as the versatile all-purpose power drill in our toolbox. It is fantastic at finding really complex, kind of twisty patterns in what we call structured data. You know, things like spreadsheets, financial records, patient health charts. It is the absolute go-to for making sense of numbers and categories, all laid out neatly.
So where do we actually see this thing in action? Well, in healthcare, it's busy fusing together all sorts of patient data to get earlier diagnoses. In the energy sector, it's predicting the stability of our power grids, which is a huge deal. And in cybersecurity, it's right there on the front lines, sniffing out network intrusions by spotting patterns a human eye would probably just skim right over. It's a true generalist.
All right, next up we have a real specialist, the Convolutional Neural Network, or CNN. This is the vision tool in our kit. It's kind of like a super-powered digital magnifying glass that's literally built to understand spatial information. It sees the world in pixels and is absolutely brilliant at identifying features, objects, and textures inside of images.
And its resume, pretty impressive. In medicine, CNNs are analyzing images to help diagnose chronic wounds. On the factory floor, they're automating defect detection, spotting tiny little flaws in products zipping down an assembly line. They're even used to optimize the output of solar panels. Basically, whenever the task involves seeing something, the CNN is almost always the right tool for the job.
Now, let's grab the memory tool, the Recurrent Neural Network, or RNN. This tool is all about understanding things that happen in a sequence. You can think of it like a tape recorder that actually remembers what came before, which gives it crucial context. And we also have its more powerful cousin, the LSTM, which stands for Long Short-Term Memory. It has a way more sophisticated memory, which allows it to recall important bits of info from way back in a sequence.
So what kind of jobs need a good memory? Well, in biomedicine, RNNs analyze the sequence of brainwaves from an EEG to figure out a person's mental workload. In cybersecurity, they look at the flow of network traffic over time to spot threats. And of course, they are absolutely essential for speech recognition, understanding the sequence of sounds that make up words and sentences.
So here's the bottom line, the really crucial point. We use different tools for different kinds of data. A CNN is the master of space. It looks at a whole picture all at once. An RNN, on the other hand, is the master of time. It processes data point by point, in order. Choosing the right tool comes down completely to the shape of the problem you're trying to solve.
But what about those really complex jobs? Sometimes a single tool just won't cut it. And that's when engineers get super creative and start building custom and hybrid tools by mashing different neural networks together in some pretty fascinating ways. So let's talk about one of the most clever combinations out there, generative adversarial networks, or GANs. A GAN is basically two networks locked in a constant duel. First, you have the generator, which you can think of as an art forger. Its whole job is to create new, fake data. Then you have the discriminator, which acts as an art detective, trying its best to tell the difference between the real deal and the forgery. The absolute genius here is the competition itself. As these two networks battle it out, they force each other to get better and better. The forger gets better at making convincing fakes, so it can fool the detective, and in turn, the detective gets better at spotting even the tiniest, most subtle flaws. It's this whole adversarial process that allows the generator to eventually create some stunningly realistic synthetic data. And this isn't just for making cool art. A model called CrimeDitGAN actually used this principle to detect digital traces inside of crime networks. By learning to generate and recognize patterns in communication, it achieved a staggering 91.23% accuracy, which just goes to show how this creative tool can be used for some really serious analytical work.
Another really cool custom approach is making our AI tools, well, smarter about the real world. Instead of just letting a network learn everything from scratch, which can be messy, engineers can embed known rules, like, the laws of physics, directly into the model. This grounds the AI in reality, making its output way more reliable for super complex engineering tasks, like controlling the incredibly precise magnetic bearings you'd find in high-tech industrial machinery.
Now, building these powerful models can take a ton of time and a massive, massive amount of data. So this next set of techniques is all about making that learning process way more efficient. How can we get our AI to get smarter, faster?
The key is this awesome concept called transfer learning. Think of it like giving your AI a head start. So instead of training a model from absolute zero, you start with one that's already an expert in a general field. Then you just fine-tune it on your smaller, more specific set of data. And the difference, as you can see right here, is just dramatic. The time and data needed can absolutely plummet, which makes powerful AI so much more accessible to everyone.
And we see this technique being used everywhere. It's used to slash training time for industrial defect detection. It helps models that analyze brain waves work better across different people, which is a tough problem. And it's absolutely crucial in medical imaging, where getting huge amounts of labeled data can be really, really difficult. Transfer learning really makes powerful AI possible even when data is scarce.
So, we've seen just how powerful these tools are. But you know what they say, with great power comes great responsibility. Our final section is all about the AI Safety Manual, the principles we absolutely have to follow to make sure these systems are trustworthy.
And this really is the central question, isn't it? A lot of these complex neural networks can feel like a black box. Data goes in one end and answer pops out the other. But the reasoning that happened in between is a total mystery. And for high-stakes stuff in medicine or safety-critical systems, it's not good enough. So, engineers have developed tools specifically to crack open that black box. One of the most important ones is called SHAP. It's an explainability technique that basically acts like an auditor, showing exactly how much each piece of input data contributed to the final decision. In that chronic wound diagnosis system we talked about, for instance, this gives clinicians really clear insights, which helps them trust and, importantly, verify the AI's recommendation.
This all really comes down to three main pillars. First is reliability, making sure the model performs accurately and consistently, like an EEG model that can detect seizures with 96% accuracy. Then there's safety, which means verifying that the model is robust in critical situations, like analyzing a car's braking system. And finally, interpretability, like we just saw, which means we can actually understand why the model made the choice it did.
So the AI Toolbox is growing more sophisticated every single day. We've got specialized tools for vision, for memory, for creation, and so much more. The ultimate question for all of us isn't just what these tools can do, but how we choose to build them and use them responsibly to create a future that we can all actually trust. Thanks for tuning in.